Okay, today we're going to talk about the chromatography lab. We'll be doing paper chromatography, but you guys can, you could do thin layer chromatography. It's a little bit more expensive because you have to buy plates. Paper chromatography, you want to use like a porous paper. You can buy chromatography paper. You could also buy chromatography paper strips. You can also test different substances. I'm going to be using washable markers today. You could do food colorings. I've done one where they test different brands of black pens. And then for this, we're also going to be doing water as our solvent. Because these are washable markers, they're going to dissolve well in the water. So on your paper, you want to label with pencil, a line just a little bit above the bottom, and you'll mark with pencil again labels for the colors of the marker. And then when you go to mark it, you're just going to do a small dot of each color on the line. The reason you want to use pencil is so that way, if there was like a pen or something, the dye itself could interact with your markers, and that could be problematic. So you want to make a dot for each of them, just on the line. If you're doing like a food coloring, you could use a capillary tube and just get a small amount in the capillary tube and dot it onto your chromatography paper. But markers are pretty straightforward. And then once you get all of your dots ready, what you're going to do is you're going to staple it. So if you have a container that works, you can set it upright. You can tape it to a pen or a pencil like this and like balance it in a container. But you want just a small amount of the paper to touch the solvent. So I don't have like a container that fits. I use beakers. So what I do is I staple it like this and just have the paper stand up in the beaker. So I just do two staples, one on the top and one on the bottom. And then our chromatography paper is ready to run. Okay, so when the solvent front is just a little bit away from the top, you want to go ahead and unfold it and use a pencil to trace where the solvent front is, because as it starts to dry, you won't be able to see that anymore. So I trace the solvent front. It might also be worth tracing your colors as well, because they're gonna still move a little bit. But you'll notice like the brown marker separated into like an orange, a purple, and a blue. The purple separated into like a purple and a blue. The red was just a single substance. Orange was just a single substance. Yellow was just a single substance. Green looks like it was also just a single one. The blue has a little bit of that purple red and a lot of blue. And then the black looks like it was a lot of red and green and maybe a little blue at the top, but that's maybe a source of error. Do you see how the black and the blue ran together? So that's going to be a bit of a source of error. Now, when you're measuring these, you want to measure from the starting point to roughly the middle of where that color is that you're measuring. And as long as you're consistent for each one, you should be good, but you'll effectively measure with a ruler the distance from the starting point to the middle of the color, starting point to the middle of the color, starting point to the middle of the color, for each individual color, not just each marker, but each color that you see. You also want to go ahead and measure the solvent front, because our solvent front wasn't the same all the way around. You want to measure the distance that the solvent traveled in a row for each of those markers. And that's going to help us calculate the RF value for each individual color. Okay, so here are the full results from our chromatography experiment. So this is the marker, and these are the individual dyes in the marker, and the distance that they traveled, the distance that the solvent traveled. We're going to calculate the RF values for each of the individual dyes in the marker. So like for this orange dye in brown, I'm going to take the 3.5 and divide it by the 7.4. And that's going to get us our RF value, which is the retention factor. So the distance that the solute traveled divided by the distance that the solvent traveled. Now in theory, if you had really, really accurate results, you would get substances that are the same molecule would have the same retention factor. So you might argue that like this pink right here, the 0.71, you might argue is the same as this pink color here, the 0.67. Because they're pretty close, or maybe this blue 0.95 could be the same as this blue 0.91. On the other hand, you might argue that the orange from the brown at a 0.47 is not the same molecule as this orange at a 0.75 because their RF values are very different. The other thing you want to conclude from chromatography experiments is looking for the one with the highest RF value, the one that traveled the furthest. That would be like the blue dye in those two markers. The ones that travel the furthest have the strongest intermolecular forces with the solvent. In this case, it was water. So they're probably going to be forming strong hydrogen bonds or dipole-dipole interactions with the water molecules, so they travel further up the paper with that solvent. We call the solvent the mobile phase in a chromatography experiment, and the paper would be the stationary phase. So all of your explanations whenever we're doing a chromatography experiment should involve intermolecular forces, which is why I like to do this experiment with Unit 3.